Okay, Hanji. Hello everybody, am I audible guys? Am I audible to you? Okay, let me check that am I audible to you or not. And after that we'll start our class. Check. Okay, so yes, I'm audible to you and visibility is also clear. So I hope that we can start our class, right? Who is watching me live? Let me know. I think everybody is enjoying Sunday. Yes. Everybody is enjoying the Sunday. So guys still get no Sunday, no Monday. Only work day. Okay. So in the previous class, so today's class is also very important, guys. Okay, and it's our lecture number 35, and we were studying the feed forward control strategy. We were studying the feed forward control strategy. So today's class is very important because these topics are, you can say, frequently asked topic in the gate, or you can say these topics are the favorite topic of the gate, and these are the topics in which most of the students are uncomfortable. Okay, and but we basically studied these topics in very simple way. Don't worry about that, and you can say there will be no any question that we cannot solve. So we were studying the cascade control strategy. We have discussed the cascade control strategy and all that. Okay, we have studied it. uh, can anybody tell me that up to which topic we have done? We have done the cascade control strategy, and basically we are discussing, we were discussing the feed forward control strategy, right? Okay, just give me a second, guys. Okay, this was the basically feed forward control strategy we were discussing, and cascade control strategy is completed from our end, right? So the discussion was that this is the advanced control strategy, in which this feed forward means that the measurement is basically from the input stream. The measurement is basically done on the input stream, because if any input is, if any input, or you can say that if any disturbance will come, that will come through the input stream. So in the feed forward control strategy, that deviation will captured through the input stream, and accordingly controller will take action so that my disturbance cannot disturb my process. So it is basically captured from the input stream only. Good morning. Okay, and beforehand my controller already took the action and my process will be at the steady state. So here the steady state is not disturbed at all, like feed backward strategy. Okay, it is clear. So in this picture you can see that it is the feed backward control strategy. In this strategy my controller will take action after my system disturbed. After my system disturbed. It is clear. So in the feed forward control strategy, what is my main motto? My main motto is whatever I have the Y, means what output, that will be equal to my set point, whatever I put the set point. It is clear to you or not? It is clear to you or not, right? Okay. So here important aspect of the feed forward control strategy is to calculate its transfer function. So just try to understand the block diagram of the feed forward, and after that we will try to calculate the transfer function for that. Okay, so it's something like that, let's suppose I have the, let's suppose this is my output Y. In this output there are two things which is added. One is your disturbance. Okay, one is your disturbance, right? And another is your process. Okay, let's suppose that the disturbance is coming into the system. Okay, this disturbance is measured, and let's suppose its transfer function is Gm. And this disturbance is going into the comparator, right? Okay, let's suppose that this is the set point transfer function. If it is given, then well and good. If it is not given, it means that the transfer function of that is 1. So this is my set point. Let's suppose it is my YSP. YSP is my set point in the controller. Okay, yeah, done. It is right, and it is basically compared. So after comparing this disturbance and the set point, there is an error generated, and that error generated is going into the controller. That error generated is going into the controller. Okay, controller will take action, and that will give signal to the final control element. Okay, it is clear. The final control element will basically make the process stable. This is the block diagram for the feed forward, guys, and it is very important. As you can see, this is my feed forward strategy. So this is the process. What are two things which is come into the process? One is the final control element output, and one is the disturbance. Okay, this disturbance is measured and it is fed back to the controller. Okay, and this is the set point. This error is generated and it is going into the this one. So you can see here that this is my set point, and this is my measured disturbance, and it is compared, error generated, it is going into the controller will take action, and it will give to the signal to the final control element. This final control element going into the process, this is the process, and the process is giving my output, right? It is clear to you. And this is my disturbance. This is basically the block diagram of it. Now I will try to find out the transfer function. Okay, so this is the D signal. So D signal is going here and D signal is going here. Okay, what is this, guys? What is this? This is the output of this transfer function. What can be the output? Output is my input into the transfer function. So this signal is DGD. This signal is DGD. Okay, now here this is the output for this transfer function, which is my DGM. This DGM, what is the output of this? It is this output is my YSP, input and transfer function GSP. It is clear. So this YSP, GSP and DGM is going into the comparator, generated the error. It is clear to you or not? And what is my error? My error is YSP and GSP minus DGM. This is the difference between them. It is clear. What is the output of GC? Output of GC is the input, which is the error, into the transfer function GC. What is the output for GF? It is my EGC GF. I hope that it is clear to you. What is the output? What is the output signal for this? Input, that is my EGC GF, and transfer function, that is my GP. Please tell me that in this particular thing you have any problem or not. It's clear or not? Please tell me. Please tell me, guys. Okay, good. Now just to make the equations here. So I can say that by adding these signal, this signal and this signal, by adding these two signal, I am generating my output. What I'm saying, by adding this signal plus this signal, I am generating my output Y. So I'll start from here, E, G, C, G, F, G, P, and I add the D, G, D is equal to Y. This is the output. It is clear. Okay, now put the value of the error here. So this is the value of error, that is YSP GSP minus DGM. So it is my YSP GSP minus DGM. This is the value of error, and the rest terms are same, EGF, GC and GP, plus DGD is equal to Y. Okay, it is clear. Now what we have to do, just open this bracket and write the required things, YSP GSP GC GF GP, and okay, plus Y. Okay, sorry. Okay, done. Minus D, GM, GC, GF and GP. I didn't do anything, you can say Aflatun here. I just try open the bracket. Plus DGD is equal to Y. It is clear to you? It is clear to you? Right? Done? Okay. Now these two signals have D. So I'll write here YSP, GSP, GC, GF, GP, and I will take D as common, and it is my GD minus GM, GC, GF and GP is equal to Y. Is equal to Y. This is my final equation, guys. This is my final equation. This is my final equation. Now, from here, just you need to understand what is my feed forward actually. Feed forward control strategy is a strategy which basically working in such a way that no disturbance can came my system. No disturbance can came into my system. So it is basically the disturbance rejection. It is perfectly disturbance rejection strategy. It is clear to you. So it is also called the disturbance rejection. So I'm saying it is that it is perfect disturbance rejection. If question is asking what is the transfer function for perfect disturbance rejection, it means that it is basically talking about the feed forward. So this is saying that my D should be 0, means the disturbance should be 0. Disturbance should be 0 in the sense that disturbance should be 0 in the process. Okay, means that process should not feel the disturbance. In the input stream there is a disturbance, but in my process should not be lose its steady state. I hope it is clear to you. So if your D is 0, what I can say, in what case your D is 0? When the coefficient of D will be 0. This in the main equation, your perfect disturbance rejection will come when the coefficient of your disturbance will be 0, then this D will be 0. So it means my GD minus GM, GC, GF, GP, that must be equal to 0. That must be equal to 0. Now, what is the question? What is the question is basically asked in the gate? What can be the question is basically asked in the gate? They'll ask you the feed forward controller transfer function for the perfect disturbance rejection. What is the feed forward controller transfer function? So very simple, through this equation I can calculate that my GC is GD divided by GD divided by GM, GF and GP. This is my controller transfer function for the feed forward control. Most of the time you will find that your measurement instrument and your final control element transfer function will be 1. So in that case, what will be GC? Directly you can write it is my GD divided by GP. This is very, very, very important. Means most of the time gate is asked this point. Most of the time. Most of the time, guys. So for the feed forward control strategy, we have two conditions, right? We have two actually a main motto here. The first motto is basically perfect disturbance rejection. Means your D is equal to 0 Second is this one, means whatever your output is, that must be equal to the set point. These are the two conditions. My output should be equal to the set point. It is clear. So by using one condition, I calculated the controller transfer function. The second type of question they asked is basically about the transfer function for the set point. What is the transfer function for this set point? Okay, what I'm saying, that they can ask you the transfer function about the controller, and they can ask you the transfer function of the set point. It is clear. So how to calculate the set point transfer function? By using the second condition. It is means the set point tracking. Set point tracking means that my output should be the set point. It is clear. My output should be the set point. So this is my equation, guys. This is my equation. It is clear. So in what scenario perfect disturbance rejection means that in this process there should not be enter my disturbance. What is this feed forward? This is my what? Controller, or you can say it is my feed forward controller. It is my feed forward controller. So this feed forward controller is basically what this controller is doing. This controller is basically rejecting this disturbance. Disturbance. It is clear to you or not? This controller basically through this action of this controller, this the error is come into the system or not? Tell me, Askar. Error is coming into the system or not? My system is disturbed. The system is disturbed. System is disturbed. If system is disturbed, then I think you did not hear me out, you can say, in attentive mind. When the system is disturbed, if the system is disturbed, then what is the point to use the feed forward control strategy? This is my feed backward, this is my feed forward. What is the difference between the feed forward and the feed backward? That is my base, you can say, concept for the feed forward, na? In the feed backward, when my controller will take action, when there is a change in the temperature of the process. Yes or no? Here, see now, where is the measurement instrument installed? It is installed in the process. So it measures the deviation within the process. It means that the process is disturbed. But here you can see where the measurement instrument is installed. It is installed at the disturbance. It is installed at the disturbance. Yes, controller takes the action to prevent the disturbance. So it is basically taking the signal from the disturbance, and if the controller finds that there is any you can say the variation, or you can say the misbehavior of this input stream, then it will already taken the action so that my system will remain at the steady state. Okay, so it is basically what this controller is doing. It is rejecting this disturbance. It is rejecting the disturbance. So one is my perfect disturbance rejection and another is my set point tracking. Okay, so there are two main motto here. Okay, perfect disturbance rejection. For that purpose, this whole term will be 0 and y equal to ysp. For this condition, the coefficient of the ysp should be 1. If you want y, whatever your output, that must be equal to your set point. For that purpose, For that purpose, we can say y equal to ysp. In what case? When the coefficient of the ysp will be 1. So what is the coefficient of the ysp? GSP, GC, GF, GP. GSP, GF, GC, FCP, FCP. That must be equal to 1. What they'll ask the transfer function for the set point. That is equal to 1 divided by FCP. FC. Okay. FCP. What is the C transfer function? It is already calculated. That is GD divided by FMP. So it is 1 divided by GF, GP. Put the value of GC here. GC is my GD divided by MFP. Okay. GF, GP. GF, GP got cancelled. What is this transfer function? It is my GM divided by GD. Okay, and if your GM is equal to 1, then your set point transfer function is equal to 1 divided by GD. Is it clear? Is it clear, guys? Okay. So these are the two things which is important in this case. Correct? So we'll see some questions based on it, and you'll understand everything. You'll understand everything. Okay. One, you can say one variation. Also, we will discuss what if in this comparator there is plus plus, means that kind of positively feedback kind of comparator, plus plus instead of plus minus. In that case, what is the impact on the transfer functions? Okay, so let's suppose this is my first kind of feed forward, and I'll take I'll copy this slide and I'll post it here. Okay, so let's suppose this is my second one. Let's suppose it is plus plus. It is plus plus. So where it is plus plus, it means my error will be YSP GSP plus DGM. It is plus DGM. It is clear to you or not? Rest everything is same. Rest everything is same. So in that case, what will be my, you can say the what will be my equations? So this is the error. So in this equation means everything is same, but in this equation this is the plus actually. This is the plus actually. That's it. Okay. So I will write this equation. I will write this equation. That is equal to YSP GSP, and we have to add the signal DGD. So this is basically error generated. Okay. Sorry. DGM. So this is the error generated, and that error is basically multiplied. This error is basically multiplied with the your controller, point control element, and the process, and that is equal to your Y. So this is the equation, if you will see, plus DGD also, plus DGD. Is equal to y. Okay, again it is my YSP, GSP, GF, GC, GP plus D, GM, GF, GC, GP plus DGD is equal to y. And for perfect rejection, the coefficient of your D, I'll do one thing. I can write this step directly. Just take out the D as common. Just take out the D as common. And for perfect disturbance rejection, this coefficient means GM, GF, GC, GP plus GD is equal to 0. What we have to calculate, guys? We have to calculate the controller transfer function now. So in that case, my GC is equal to minus GD divided by GM, GF and GP. Okay, and for GC is equal to minus GD divided by GP when your GM and GF given is unity. Right? So you can remember this formula. You can remember this formula, and accordingly, if any M and F value is given to you, accordingly you can put that value. Okay, it is for the plus plus. For the plus plus, there is a negative sign. For the plus minus, there is a positive sign. There is a positive sign. It is clear? Okay, tell me, set point transfer function will change or not? In this case, my GSP change or not, guys? Or it will be same? Or it will be same? Change. Okay. What will be the value for it? What will be the value for it? And why it is change? Why it is change? Why it is change? Negative. Why it negative? Why it's negative? Okay. So let's solve this. Okay, so yeah, my GSP is equal to 1 divided by GF, GP, GC. Put the value GC, it is my minus GP divided by GF, GP, GD. GP, GP got cancelled. GSP is equal to, if GF is equal to 1, then it is my 1 minus 1 divided by GD. If your GF is equal to, okay. So these are the very simple things. Now, one important thing is that in gate questions, if in the block diagram, if you will see plus in the comparator, plus minus, if you will see the plus minus in the block diagram, then treat it as a, then use those formulas, whatever we discussed. Okay. If nothing is given to you, then treat it as a plus. Okay, then treat it as a plus. Okay, so let's take some question. This is my GATE 2014 question, and just see this question. What is this question saying? Given below is a simplified block diagram of a feed forward control system. You can see this is my disturbance, transfer function, this is my output, this is my plus, this is my process, and this is my GF. What is the GF actually? GF is not the final control element, guys. See, the transfer function of the process is G. So my GP is given to us. GP is equal to 5 divided by S plus 1. And the disturbance transfer function is GD is equal to 1 divided by S square plus 2S plus 1. I can write it as S plus 1 whole square. It is clear? And that what is question saying? See, the transfer function of the perfect feed forward controller GF. So here GF is my actually controller transfer function. It is my controller transfer function, not final control element transfer function. Here notations are differently used. Okay, no worry. And you can say that if other transfer function is not given to you, it means that all their transfer functions are 1. No problem at all. Here notice, you can say YSP is given here, no problem. No GSP is given, no problem. No final control element transfer function is given to 1. Let's suppose it is my 1. Rest is 1. This is my controller. So how to find out the controller transfer function? Controller transfer function, how to find out? So yeah, this is my controller transfer function. That is equal to minus GD divided by GP. Minus GD divided by GP. Minus GD, that is 1. Okay, I'll write it. Minus GD divided by GP. Minus 1 divided by S plus 1 whole square. And divided by GP. GP is equal to 5, and it is my S plus 1. It is clear, S plus 1, and it's gone. My GF is equal to minus, it is my GT divided by GP. It is my minus 1 divided by 5 into S plus 1. I think C is the correct option for this. C is the correct option for this. Okay. Next. This is a recent GATE tier question to 2024-2024 question. So as I told you that this topic is very favorite topic for the GATE. So again, this is my D, you can say this is my D, and this is my controller transfer function GC, feed forward controller. This is the feed forward controller transfer function. This is my process transfer function. This is my GP. Okay, and it is added and it is giving me the output. I have to find out the value of K. What is the question? I have to find out the value of K and alpha divided by beta. Alpha divided by beta. It is very simple, yeah. Find out the transfer function for the controller and compare the value. After comparing the value, find out the value of K, alpha, beta, and calculate the required parameter for the question. No problem at all. So again, what is my controller transfer function? It is equal to minus GD divided by GP, and everything is given to you. GD is this, so it is my minus. Okay, see, in this question there is nothing given to you that what is this transfer function. You should know about this diagram. This diagram is also important, guys. You can clearly see that this is my GD. It is clear to you? Okay, so GD is my 1 divided by S plus 1 whole square. Okay, and divided by GP. So this is my GP. GP is equal to 2 divided by 0.5 S plus 1 whole square. It is clear? Just do one thing. Just simplify this. And simplify this according to this format, because ultimately I have to make it GC in this format. So GC is equal to minus 1 by 2, and this C, there is a numerator, there is a denominator, and its whole square. So it means that it is 0.5 S plus 1 divided by S plus 1 and its whole square. I think now you can compare these values. I think now you can compare these values and find out the whatever they are asking. Okay, what is my function? What is the general format given to us? That is equal to K into alpha S plus 1 divided by beta S plus 1 and its whole square, right? So just make sure it is plus 1 plus 1. Yes, it is plus 1 plus 1. What is my K? K is equal to minus half. It means it is my minus 0.5. What is the alpha value? Alpha is my 0.5. What is beta? Beta is equal to 0. Beta is equal to 1. Beta is equal to 1. Now what is my alpha beta? So K is equal to minus 0.5 and my alpha divided by beta is equal to 0.5. So yes, B is my correct option. B is my correct option. Got my point? Got my point, guys? Okay. Good. Okay, let's take another question. Let's take another question and we will move to towards the next topic. Tell me the answer. Tell me the answer and we'll move forward. Okay, option C. Yeah, C is the correct option. C is the correct option. So I have to find out the feed forward controller transfer function. Again, very simple. I know that my GD is equal to minus GC, or see, here is no plus and minus sign given here. Okay, so there is no need to put the negative sign. Okay, because here we do not have the, you can say, your block diagram. So accordingly options we have to proceed. So it is my, what is my what is my GC? GC is my GD divided by GP. What is my GD? GD is 1 divided by 2s plus 1 and 5s plus 1. And what is my GP? That is my 2s plus 1 and 5s plus 1 divided by 2. These could cancel. What is it? It is half. Means it is. So C is the correct option. So you can see here that there are very simple problems we can say based on the feed forward controller transfer function, and multiple times the feed forward controller transfer function question is asked in the gate examination. So this will be my important from the examination point of view. Okay, great. Now let's try to understand both parallelly, the feed forward and the feed backward. Feed forward and the feed backward. Okay, it is clear. So as I told you guys that whatever we discussed previously, that is basically the feed backward. That is the feed backward. Now it is my feed forward is my, you can say, the advanced control strategy. Feed forward is my advanced control strategy, and you can see here that in what sense we are saying that it is the advanced control strategy. It is clear. It is clear. So feed forward and feed backward. So please, you can put the heading, the advantages and disadvantages of feed forward and the feed backward. Feed forward and the feed backward. Feed forward and the feed backward. Okay, let's try to understand it. Okay, so I hope that both the strategies are clear to you in terms of the block diagram, in terms of the concept. Now in what sense we are saying that this is the advantage and this is the disadvantage, just try to understand it. First of all, let's try to figure out the feed forward. What is the advantage and what is the disadvantage? See, very simple guys. The advantage of the disadvantage of the feedback will be the advantage of the feed forward. Okay, what I'm saying, disadvantage of the feedback will be the advantages of the feed forward, and the disadvantages of the feedback, it will be the disadvantage of the feed forward. See, first of all, we know that feed forward advantages, it acts before the effect of a disturbance has been felt by the system. We know that feed forward is a perfectly disturbance rejection system. It basically prevents the disturbance to come into the system. One point is its advantages, and this is the disadvantage of the feedback. It waits until the effect of the disturbance has been felt by the system before control action is taken. So we know that in the feedback, system is disturbed, after that control will take action. So you can say instability is introduced in the system. Now that is a disadvantage for us. Second, is good for slow system or with significant dead time. So feed forward is good for the slow system. Feedback is it is unsatisfactory for a slow process or with significant dead time. So it is basically unsatisfactory for the slow process. Like if the temperature is slowly increasing, accordingly that increasing pattern continuously control will take action. So sometime it will increase, sometime it will decrease. So by this you can say action, my process is not that much stable. So this is its advantage. That's the disadvantage. It does not introduce instability in the closed response. Yes, we know, and it may create instability. It is already known to us. Now its disadvantage and its advantage. Now, what is the feedback advantage? It does not require identification and measurement of any disturbance. It does not require identification and measurement of any disturbance. सही बात है. It's correct thing. See. This is my feed forward and this is my feed backward. Here the measurement is of only the temperature. Here measurement is only of the temperature. This temperature change may be due to the change in the flow rate of the input stream, or maybe the change in the temperature of the input stream, or maybe any other parameter. But in this strategy, it does not care. It does not care about what is going on in which parameter of the input stream. It only takes care the what is the temperature change within the system. It is only worried about the temperature. That's it. But here, this variation can be in anything. Yeah, this variation can be in the flow rate. This variation can be in the temperature. Any parameter. It is clear. This variation may be in the pressure. So this is the measurement actually. So this measurement is in the feed forward. This controller, or you can say this measurement has to be you can say programmed like that this is measured every parameter. If the flow rate will change, this has to be measured. If the temperature change, this has to be measured. If the pressure change, it has to be measured. So it requires the system information. It requires the identification of all possible disturbances and their direct measurement. It is clear? So it does not require, and it requires. It is insensitive to modeling errors. Yes, it is insensitive modeling errors. In the disadvantage, it is sensitive. It is sensitive. Okay? And it cannot cope with the unmeasured disturbance. Some disturbances are unmeasured, means you cannot directly measure that those disturbances, like concentration. Have you seen any instrument which can directly measure the concentration? Like to measure the flow rate, there's a flow meter. To measure the temperature, there is a thermometer. Lot of instruments are there. But to measure the concentration, there is nothing, you can say, kind of meter. Okay, so if it is not measured, then those disturbances are called unmeasured disturbance. So we cannot apply the feed forward for that. It is insensitive to parameter change, as I already told you that all this is you can say, in other words, it is a first point itself. Sensitive to process parameter because it is require all the identification, and it require the good knowledge of the process model. So these are the feed forward, feed backward, advantage, disadvantage in the PSUs, or also in the you can say in the gate examination, they can ask the 1 mark question based on it. Okay, so you can see this. Can we move forward? Please tell me. Can we move forward? Okay, great. Now, please put the heading poles and zeros. We already discussed about the poles and zeros. Okay, but let's discuss it further because I need the poles and zeros for topic. Please put that in poles and zeros. Let me know that what are the poles and zeros. Let's understand again this. Let's suppose I have a transfer function, guys, like gs is equal to ys divided by xs. This is my transfer function. Okay, it is clear or not? Or any equation a in the s divided by bs, whatever it is with any notation. What are the zeros actually? What are the zeros? Zeros is basically denoted by m. What are the zeros? Very simple. The zeros means the value of the s on which my transfer function is 0, or you can say that if my ys is equal to 0, then this transfer function is 0. It is clear to you or not, right? So if I put numerator as 0, then my transfer function will be 0. Is it clear to you or not? Now put ys is equal to 0 and find the values of s. Find the values of s means you have to find out the roots of the numerator. What are these the values of s? These are the roots of numerator. So roots of the numerator are the zeros. Roots of the numerator are the zeros. Likewise, poles. What are the poles? Poles is the value of s at which my transfer function is infinity. When it will be infinity? When xs is equal to 0. Right? So put x is equal to 0 and find the values of s. What is the meaning? What are the poles? Poles are the roots of denominator. Roots of denominator. These are the poles. It is clear? Please write it, and we will take a very simple question, and after that we'll move ahead. I hope that you done with this. Okay. Let's take an example, guys. Let's suppose I have GS as s plus 3 divided by s minus 2 and s plus 2. Question is find zeros and poles. Find zeros and poles. Okay, very simple. For zeros, you have to put numerator as 0. S plus 3 is equal to 0. Correct? So what is the value of s? S is equal to minus 3. S is equal to minus 3. So this is the root of the numerator, which is called 0. If somebody is asked how many zeros are there, number of zeros, means what is the value of m? M value is equal to 1, right? How many zeros are there? 1. Okay. What about the poles? For the poles, the denominator will be 0. So s minus 2, s plus 2 is equal to 0. So s value will be 2 and minus 2. 2 and minus 2. It is clear to you? So these are the roots which are called poles. And how many poles are there? Number of poles 2. Number of poles is n value is equal to. Okay, and don't confuse. Do not confuse this 2, 2. Don't confuse. Okay. Let's suppose it is 4, 4, that is equal to 4, 4, and 4 minus 4. 4 minus 4. Okay. So how many poles are there? 2 poles are there. How many poles are there? 2 poles are there. It is clear? Okay. Let's take another example. See, guys, just remember one thing here. As also from the route information, we are aware about it that for stable system, poles must be negative. Poles must be negative. It is clear to you or not? What are the poles? Poles are the denominator roots. Denominator is my characteristic equation. If those are negative, it means that roots lies on the left side of the imaginary axis, and that will be the stability condition. Is it clear? For example, if I have transfer function as 1 divided by s minus 1 and s plus 2, what is the roots of it, or you can say what are the poles? Poles is equal to 1 and minus 2. So one pole is positive and one pole is positive, one pole is negative, or you can say one root is positive, one root is negative. It means one root lies on the left side of the imaginary real axis and one is on the right side of the imaginary real axis. It means that this system is unstable. This system is unstable. It is clear? And let's suppose I have my GS as s plus 1 divided by s plus 2 and s plus 3. So what are the poles? S is equal to minus 2, minus 3. So all the roots are negative. It is clear. So it means that they fall on the left side of the real axis. So it is my stable. So these are in the terms of poles and zeros. Okay, these are in the terms of poles. It is clear. So if your poles are negative, then your system will be stable. Otherwise, it will be unstable. So this is in the terms of the poles. So these are the information about zeros and poles, which is very, very important for us to understand the next topic, that is called inverse response. I think in the class when we were studying the class 11 or 12, you were asked that what is the inverse response. See, these are the last topics. These are the, you can say, last topics. So please write inverse response and we will try to understand the meaning of inverse response. Inverse response. In your notes, just make this flow diagram as like that. Let's suppose this is my drum. This is my inlet, cooling water inlet, and there is some liquid, there is some vapor, okay, and there is a steam. This is steam inlet, this is the steam outlet. This kind of diagram you can make. Please write inverse response. And this topic is very, very, very important. Nowadays this is the favorite topic of the gate. Okay, they are asking the questions regarding the inverse response. If you'll see the previous questions, then you will not find, so you can say, the frequent question on the inverse response, but in the recent years it has been observed that inverse response question is, you can say that there are high chances that you'll find the inverse response question. Now just try to understand what is the inverse response. Inverse means ulta, opposite. Response means response. Inverse response means opposite response. Means that result is not same as I'm expecting. Like, I have given you some homework. My expected response is that you'll do the homework sincerely. But your response is like that, instead of doing the homework, you are basically tearing your notes. You are disposing your notes. So this is totally inverse response. It is clear. So in this way, just let's try to understand it. Here, just focus on the two streams, which is very important for us. That is my cooling water inlet. Just focus on the two stream, cooling water inlet and my steam. Actually, this is my kind of boiler in which I am generating the steam. So for the generation of the steam, there are two things required. One is the water and another is the heat, which can convert that cooling water into the steam. Very simple. So this is my cooling water inlet from which my water is coming into the system, and this is the heat which I'm giving to this cooling water, so that this water can be converted into the steam. Very simple. Now just try to understand it. One thing, if you will see that cooling water inlet, let's suppose this is the steam. You can see that this is the steam level. Okay, you can see this, right? And this is the water level. Tell me only one thing. What is the ability of cooling water inlet? Ability of cooling water inlet is to increase the level of the steam, or it is the decrease the level of the steam? Please tell me. Means if you increase the flow rate of the cooling water, the steam level will rise or steam level will you can say fall. Steam level will fall. If more and more cooling water will going into the system, what we can say, guys, I'm asking, yes, I'm asking that what is the ability of the cooling water? If more and more cooling water is coming into the system, the steam level will rise or fall. The steam level will rise or fall. See, just I think you guys are confused. Just try to understand. Fall if the hot stream is same. Yes. So if cooling water is coming into the system, it means that there is a more condensation. There will be more condensation here. Means the steam will condense and the level of the steam will be fall. The level of the steam will be fall. It is clear. The steam So this has capacity to decrease the level of the steam. Okay, and what is the this steam coil function? It will basically rejecting heat to this water, so that more and more steam will generated. So the function of the steam here, the steam coil, is basically to increase the level of the steam. It is clear to you? So cooling water is basically, effect of the cooling water and the effect of the steam is opposite to each other. It is clear? So let's suppose this is my output. Let's suppose this is my time. Cooling water impact is that it is basically this is the impact of the cooling water. So see what will be happen actually. This is the cooling water impact, that it will basically decreasing the level of the steam, and after some time it is basically you can say towards a constant value. It's not something like that continuously it is decreasing the steam level, because continuously steaming is coming into the system, so heat transfer will occur and steam level will not continuously fall down. It is clear? What is the effect of this steam heat coil? The steam heat coil function is to increase the level of the steam continuously. It basically increase the steam level. It is clear? So this is basically continuously decreasing the increasing the steam level. So this is basically representing the heating. These are the separate effect of these two streams. Cooling water inlet. What is the function for the cooling water inlet? What is the function for the cooling water? It will decrease the level of the steam continuously, and after some time it approaches a constant value, means with respect to time the rate of decrement in the steam level will be less. What is the function of this steam coil? Steam coil is basically rejecting the heat to the water, so that continuously my steam will be generated, means it is basically continuously giving heat to the system, and it is basically doing the work of heating. It is clear? Now just try to understand it, what will happen. There is a fixed steam is coming into the steam coil, and the cooling water inlet is also some water is coming into the system. Let's suppose the cooling water inlet, we increase the flow rate for the cooling water. Flow rate which is coming into the steam drum. Now what will happen? Just try to understand it. Initially the steam will be condensed by contacting of the cooling water inlet, but after some time, because my steam heating coil will be continuously giving the heat to the system, after some time my steam generation will be more, or you can say my steam level be my steam is forming, or you can say my how to make you understand. Okay, just see. Cooling water, when the cooling water is coming into the system, initially condensation will be more, because more and more cooling water will come into the system. So at the first stage, my steam level will be decreased. What I want my steam level will be increased. It is clear to you, because this is the boiler operation, and I want the conversion of water to the steam. So initially my steam level will be decreased. Now see the steam heating coil action. After some time, the heat transfer will occur between the cooling water and the steam coil, and again the steam level will be rise. So cooling water is basically decreasing the level, and steam heating coil will increase the water level. So these are the two opposing effect. It is clear? If you combine these two effects and we'll see what are the overall response, then overall response you will see that initially the level of the steam will be decreased. Initially the level of the water will be decrease, but after that it will increase. So this is the overall response. These are the individual response. This is the steam coal response, and this is my cooling water response. It is clear to you? This is called inverse response. So if you will see here that I want that my steam level will increase, but initially if I'll see that response will be in the opposite direction. Instead of increase the steam level, it is decreasing. That's why it is called inverse response. But overall it is in the positive direction. I hope that this funda is clear to you. Yes, it is clear. So I will write here, if initially the response is in the opposite direction to where it eventually ends up such behavior is called inverse response. Okay, and this is also called known minimum phase response. In the inverse response is a practical or a no, it is practical. It is practical. Whatever I'll give you this example, this is the practical example. This is the practical example. Done. Uh, we are not using the inverse response in the industry. This is the effect. This is actually the effect. We are not using anywhere. We are not basically this is not the planned activity. Okay, this is not the, you can say, in our plan. This is not any, you can say, modeled activity. This is actually a response. Some system shows these kind of response. In the industry also, you can, whatever we discuss this example, this is the boiler operation example. This is a boiler operation example. So we do not want that my response will be inverse. No, it is the response shown by the some process in the industry, and these are the inverse response. Okay, we are not using it. These are the response shown by some process. Okay, so here there are two processes, as I told you that there's a cooling water and there's a heating. These are the two processes. Okay, it is clear. Let's suppose this cooling water is my, let's suppose, purely capacitive. Means there is no resistance at all in this cooling water inlet. It is continuously coming into the system. It is continuously coming into the system. It is clear. So I can say that I have 2. Let's suppose one process is purely capacitive, right? And let's suppose that there are two inputs. So this is actually the overall input. This is my overall input, right? And these are going into a comparator and generating a final output. Okay, it is clear. One process is your first order process. Let that heating is your first order process. First order process transfer function is K1 divided by tau 1 S plus 1. And one process is purely capacitive, and purely capacitive transfer function is K2 divided by S. So these two transfer functions combined with each other and generating a overall output for this. It is clear or not? It is clear or not? So this is my purely capacitive, this is my first order system, and it is generating the output, overall output. This is my overall output. This is showing the purely capacitive, this is showing the first order system. This is my purely capacitive, and this is my first order. This is my input. So there is some output through this transfer function, and there is some output through this transfer function, and by comparing these output, I am getting the overall output. I am getting the overall output. These are the full case. So what will be output? Output will be the comparison between these two transfer function. So output will be my K2 divided by S minus K1 divided by tau 1 S plus 1. Okay, I take the LCM, that I can take S into tau 1 S plus 1, and it is my K2 into tau 1 S plus 1 minus K1 S. Okay, just what to do? Just expand the this numerator. It is my K2 tau 1 S plus K2 minus K1 S divided by S into tau 1 S plus 1. It is clear or not? I can write it as, how to write it? It is my S term K2 tau 1 S minus K1 S plus K2 divided by S into tau 1 S plus 1. Okay, now I'm going to write a very, very important thing, and you have to remember this thing. It is a very, very important case. This is the one line which is very, very important, and from the gate point of view, it is very important. For the stable system, if we will talk about the zeros, then there must be the positive zeros for inverse response. So it has been found that any system can show the inverse response if there are positive zeros. So this is the mandatory condition for the inverse response, and so many times the question is asked only on this statement. Even in the 2026, this is the 1 mark question, that for the inverse response, what are the zeros? Positive, negative, and what? So there must be the positive zeros for the inverse response. This is a very, very important statement. This is a very, very important statement, and using this statement, I am calculating every condition for the inverse response. So what are the zeros? Zeros are the roots of the numerator. You can say, if I'll put numerator as 0, if I'll put numerator as 0. So this is my numerator and it must be positive now. Just give me a yes. So what I'm saying that zeros are the positive. Zeros must be positive. It is clear to you or not? So this is my transfer function. It is my k2 tau 1s minus k1s plus k2 divided by s into tau 1s plus 1. It is clear or not? Can I write this? If I put s common, if I keep common as s, k2 tau 1 minus k1 k1 plus k2 divided by s into tau 1 s plus 1. It is clear? So for zeros zeros must be positive. So do one thing, for zeros I can write that it is my s into k2 tau 1 minus k1 plus k2 is equal to 0. First of all, find the roots, and that root must be positive. S is equal to minus k2 divided by k2 tau 1 minus k1. In what scenario it is positive? See, the numerator is my negative. If this denominator is negative, negative will cancel, s will be my positive. It means I can say you have the positive 0 if this denominator is less than 0. For positive zeros, k2 tau 1 minus k1, that must be less than 0. It is clear? It is clear or not? Yes or no? And or I can say that my k1 is greater than k2 tau 1. It is clear? Or I can say that my k1 divided by k2 must be greater than tau 1. Must be greater than tau 1. It is clear? So this is my first condition for the inverse response. This is the condition for the inverse response. Got my point or not? Got my point or not? So this is my first condition. It is clear. Is it clear or not, guys? Okay, so this is the condition for the inverse response. This is the condition for the inverse response if your one process is purely capacitive and one process is your first order. Is clear? This is the condition for the inverse response. Okay. Let's suppose that we have two first order processes. Okay, so in the previous example there are two processes in which one is purely capacitive, other is first order. For these two processes, showing the inverse response condition is k1 upon k2 must be greater than tau 1. That's it. Most of the time they'll ask the question about when two first order system to first order system is in the inverse response setup. Okay, so let's suppose I have two first order system. This is the transfer function for first one, and this is the transfer function for the second one. This is my input. And this is going. Plus, minus, and this is my output. It is clear, right? So these are showing the you can say inverse response. So for that, what we can do here, this is my k1 divided by tau 1 s plus 1 minus k2 divided by tau 2 s plus 1. It is clear. Okay, take the LCM, guys. It is my k1 into tau 2 s plus 1 minus k2 into tau 1 s plus 1 divided by, it is my tau 1 s plus 1 and it is my tau 2 s plus 1. It is clear. It is clear. Okay. So just expand the numerator. My numerator is k1 tau 2 s plus k1 minus k2 tau 1 s minus k2 divided by tau 1 s plus 1 and tau 2 s plus 1. Okay, clear. It is clear, guys. So this is my numerator. Again, we will do the same thing. Just write down the s term collectively. So I'll write this as k1 tau 2 minus k2 tau 1 into s plus k1 minus k2, and that is equal to 0 to find out the zeros. Okay, and for positive zeros, first condition must be that coefficient of the s will be the negative, let's suppose. Okay, so that if it will going in the RHS, then it will make positive. So k1 tau 2 minus k2 tau 1 is less than 0. It is clear. So what is it? It is k1 tau 2 is less than k2 tau 1, or we can say that tau 1 divided by tau 2 is greater than k1 divided by k2. Okay, it is clear. So this is my first condition. This first condition is valid only if this is positive. If this is positive, then second condition will come from here, that if k1 minus k2 must be greater than 0, or we can say that k1 is greater than k2, or we can say that k1 divided by k2 is greater than 1. This is my second condition. It is clear. If I add these two conditions, this one condition and two condition, I can write that my tau 1 divided by tau 2 is greater than k1 divided by k2 is greater than 1. This is the overall condition for the inverse response if the two first order system are in the showing the inverse response. As you can see here again, that this is the response of the process 1, and this is my response of the process 2, and if I combine them, it is my overall response which is showing the inverse response. Is it clear to you or not? It is clear to you or not? Initially, if you will see, initially the process 2 is faster as compared to the 1. Initially the process 2 is faster as compared to the 1. That's why in this region overall all will be in the towards the opposite side. Initially the overall will be in the opposite side. Why? Because initially it is faster as compared to this, but overall if you see after that, my response process of the 1 will be faster as compared to the 2. Is it clear? It is clear. Okay, so guys, this is the, you can say, pace. You can calculate every condition if you want, like purely capacitive minus first order we already discussed. 2 first order response we have already discussed. If you want, you can remember the condition for this, and this, whatever you want. Okay, but till now the question is only asked on the 2 first order system responses. Okay, so if you want, then I think you can remember 3 and 4 because condition is same. That, sorry, yeah, 3 and 4 condition is same. K1 greater than K2, K1 greater than K2. That's it. It is clear to you. This is also K1 greater than K2. This is also K1 greater than K2. So you can say that this is the common condition. You can remember K1 is greater than K2. K1 is greater than K2. It's clear. But this is the basically important, which is asked multiple times. We will take some question based on it, and after that we will come to again that topic. Okay, so please see this question. What is the question? Which of the following transfer function corresponds to an inverse response process with a positive gain? So we have 4 options, out of which we have to calculate which one is showing the inverse response. As you can see in the A, B, D options, we can directly see that these are the options related to the first order system which is showing the inverse response. For that we have to calculate it. When the 2 first order systems are showing the inverse response, that the mandatory condition is tau 1 divided by tau 2 is greater than K1 divided by K2 is greater than 1. Means these ratios should be greater than 1. These ratios should be greater than 1. I'll explain this question in very detail by choosing every option so that this inverse response topic will be very clear to you, because this is very, very important. So I will, you can say, whatever we discussed till now as a concept, I will introduce all the concept. I will inserted all the concept in this question. Okay, and otherwise, if I'll solve this question, I'll solve this within the 30 seconds. That's it. Just take the option A. What is the tau 1 for the option A? Tau 1 is equal to 2 and tau 2 is equal to 3. What is the ratio? Tau 1 divided by tau 2 is equal to 2 by 3, which is less than 1. So my A cannot be the right answer. What about the B? B, tau 1 is equal to 1. Tau 2 is equal to 1. Yes or no? Tau 2 is equal to 1? No. You have to be very clear about it, guys. Just do not, you can say, do the silly mistake here. It is my divided by 10, divided by 10 and divided by 10. This is now first order system. So tau 2 is my 0.1. Tau 2 is my 0.1. What is the tau 1 divided by tau 2 here? Tau 1 divided by tau 2 is equal to 1 divided by 0.1, which is my 10, and which is greater than 1. So yeah, this can be the answer. This can be the answer. I don't know this is the answer or not. This can be the answer. I have to find out K1 divided by K2 also. See, you cannot say by seeing only a one parameter. You have to satisfy both the condition. Okay. What is the K1? K1 is equal to 2, and what is the K2? K2 is equal to 0.5. K1 divided by K2 is what? K1 is my 2 divided by 0.5. What is it? It is my 4, which is greater than 1. It is clear to you or not? So yes, that B can be our answer. B can be our answer. Okay, I'm not saying that it is answer. Why? Because I only satisfied these conditions, but I do not know about the positive gain. That this is showing inverse response with positive gain or not. I don't know. What about the option D? Let's try to understand the option D also. Option D, tau 1 is equal to 1 and tau 2 is equal to 2, which is my 0.5, which is less than 1. So it means that it is very clear that my answer cannot be A, my answer cannot be B, my answer can be B, or I did not discuss about the C. It may be possible that C is also my answer. C is also my answer, but my C is in different format. My C is in the different format actually. That's why I cannot say that this is the answer or not. Okay, let's discuss. That's why I'll discuss this at the last. So let's try to understand the option C also. Okay, so we will check the option C with a different, you can say, thing, because it is not in the standard format. Okay, so till now I know that B can be my answer. B can be my answer, or it may be possible that C can be my answer, but A and D for sure is not my answer. Now you have to calculate the gain. Now you have to find out the gain actually. If B also satisfied the positive gain, then B will be my for sure answer. B will be my for sure answer. It is clear to you? What now? The question is, what is the meaning of positive gain? What is the meaning of positive gain? Positive gain means the overall KP. Positive gain means the overall gain. It is my overall gain. What is the overall gain? How to calculate the overall gain? What is your K1 minus K2? That must be greater than 0. This is your positive gain. This is the condition which we calculated, if you remember. It is clear. What is my K1? K1 will be my 2. What is the K2? K2 is my 0.5. It is my greater than 0. So this is my positive gain. So B is my correct option. B is my correct option. It is clear to you or not? So you did not check C, not even the tau 1 divided by tau 2 condition, not even with the positive gain. It may be possible that C can be answer. Yes, C may be answer. Let's try to understand it. Do one thing, just try to calculate its gain. Take the option C. C is my 3 into 0.5 s minus 1 divided by 2s plus 1 and s plus 1. So it may be possible that this is after LCM, that this is the expression. Do one thing, find its gain. Try to calculate its gain. Okay. How to find out the gain? So I told you that steady state gain is basically defined that it is my final value for, it is my, you can say, sorry, ultimate value for unit step input. What is the unit step input? 1 by s. So this is my transfer function. Right, and multiply with the input. How to find out the final value? UVR, just applying the FVT. How to find the FVT? Multiply with the S, and S tends to 0. This is my FVT. S got cancelled. This is my 0. This is my 0. This is my 0. It is my minus 3. So this is my negative gain. This is my negative gain. So C cannot be our answer. So what is my answer? My B is answer. So every time there is no requirement to check every option. Okay, and you can say that I will also tell you that how you can calculate the question, this in very few minutes, or in few seconds. C is a very different type of option. So you need to check C in at the last. If you are sure about A, B, and D that no, these are not showing the inverse response, then you can check the C. Otherwise, don't check the C because in the you can say simple format you can find your answer. Like if I'll check B, the B will be satisfy both the condition. There's no need to check other option. I'll take the B. I'll take the B. Yes. Next question. Which of the following transfer function upon a unit step change? Unit step change is a disturbance at t equal to 0 will show a stable time domain response with a negative initial slope. Negative initial slope, as we know that initially in the inverse response there is a negative initial slope. Okay, so means that the question is basically want to ask you that which one is showing the inverse response. That's it. So again, that I'll choose the first one with the A because or in the every this plus plus plus, in this only there's a minus. First check the option A. What is a tau 1? Tau 1 is equal to 1. What is a tau 2? Tau 2 is equal to 1 divided by 4. 1 divided by 4. It is clear. So what is my tau 1 divided by tau 2? Tau 1 divided by tau 2 is equal to 4, which is greater than 1. Seems good. There's no problem. Okay. Also that my K1 is equal to 1 and my K2 is equal to 1 by 2. So my K1 divided by K2 is equal to 2, which is greater than 1. So there is no need to find other options. My A will be the answer of it. My A will be the answer of it. It is clear. It is clear. Now, okay. Also, here we can check, it will show the stable time domain response. Means by, okay, it is showing the inverse response. Now we have to check that this is showing the positive, this is showing the stable response or not. Stable response or not. Okay, how to check the stable response or not? For the stability, there must be a, we can say the negative poles. Okay, what are the poles? Poles are the roots of the denominator. What is the denominator? Denominator is equal to 0. What is the denominator for it? It is my s plus 1 and s plus 4. So s is equal to minus 1 minus 4. So poles are negative. It means negative poles. So it is stable also. So A will be my answer. As you can see, guys, here when important thing you can see that see, just try to understand a very important thing here that will help you to solve this question. By seeing these curves, what you can say, think about it. I can think that this is the response 2 and this is the response 1. If see, tau 1 divided by tau 2 is greater than 1. It means that tau 1 should be greater than tau 2. Tau 1 should be greater than tau 2. So in the question itself, just see the tau only. So here it is my 1 by 4. It is my 1. So it is my 1. This is greater than 1 by 4. Yes. Okay. Then it is satisfied the 1 equation. It is clear. So without solving also, just you can compare the tau's value. It is clear. Also K1 is greater than K2. Without solving, you can compare the K1 and K2 value for the inverse response. It is clear. So this is how you can calculate the inverse response question. So guys, this is it from my side. Okay. And in the next lecture, we will discuss the Cohen-Kuhn method. process reaction curve, and we'll solve some question. Whatever the search the question based on the inverse response in your PYQ book and solve those questions. Okay. चलिए फिर. So that's it from my side for the today's class, and let's meet in the next class. Thank you so much. Bye bye and take care. Okay.